inviting all the panelists here to join me. I would like, before to present a little bit the result of one of our work packages, work package 4, in the HO project. We have seen in the previous presentation how important it could be to digitalize network. And we have also seen that there are some power that has to be extracted from energy harvester in order to support this digitalization. My goal here is to show you that we are working on this, but it is not really an easy task. In particular, we have already discussed on the resonance condition, and we have seen, I have already told you that to trigger this resonance, we need to generate a vortex shedding downstream a body, like in this case with the cylinder, and the vortex is generated downstream. We have to enable the movement of the body in order to have this vibration that we want to extract. And we need to connect the movement of the body with a generator, with an electric machine capable of extracting energy. But this is not enough to produce energy, to produce a reasonable amount of energy, because we also need to synchronize all these things all together. So we need to synchronize the vortex shedding frequency with the natural frequency of the body immersed into the fluid. And we have also to consider in the design procedure the contribution of the electric machine and of the damping of the control system, which cause a damp on the body motion. So to put everything together and to design this harvester, we really need to approach this as a multi-physics problem. We have done this. We have considered also the constraints related to the pipe dimension, to the needs of the water distribution owner that have to provide a service. And we have put everything together, defining a design process. I do not want to bother you and to annoy you entering into all the details of this procedure. I would like just to give you an overview of the different steps. The input in this context is the fluid velocity that we want to exploit. And then there are 3 phases. We need to study the fluid, the interaction between the fluid and the body. We need to study the characteristic of the body itself, so its geometry, its materials, and how this characteristic interacts with the fluid motion, with the flow field. And then we have to integrate everything into an analysis of the electrical behavior and of the behavior of the control system. All these things have to put together in one model, helping us, supporting us in the design phase. To do this, we have done a really huge number of numerical simulation in order to create a database telling us how the body behaves inside the fluid flow. This has provided us a quite insight on the possibility of creating oscillation in the body, on achieving lock-in condition, and on the factor affecting this lock-in condition, the dimension of the cylinder, the material that has to be used, the damping effect, the stiffness of the system, and so on. And this has given us the possibility of building a graph and of on obtaining data as this one, analyzing the influence of the material of the cylinder on the possibility of extracting energy. We have done the same from the structural point of view, analyzing the structural behavior. Even in this case, we have done a lot of numerical simulation and also experimental tests to see how the body reacts if there is a fluid dynamic forces on it. And then, of course, also the electrical behavior. We have characterized the behavior of patches glued on the body in the piping configuration. We have also developed an innovative linear generator to extract the energy from the oscillation of the body itself. And at the very end, we were able to build the prototypes. Here you can see, I already shown you the prototype of it has to be installed in pipes. And then the prototype under test in Brno, in Czech Republic, for channel application. And this is the future, what we are going to do, a prototype to manufacture and to be used in open channel. And at the end of our activities, we have this nice application, I would say. In this application, you can choose the configuration you want to investigate, piping in the middle, open stream and open channel. And after the choice of the configuration that you want to design, you need to also set the type of design that you want to do, because you can choose if you want to design the device for a very specific velocity, like a constant velocity available in a certain condition, or you can also choose to design over a range of possible velocity, like the one we have seen in water distribution network, where the velocity is not constant. And you have also to choose the target velocity. So we have an optimization procedure telling us also the velocity that has to be chosen for the design development. And then there is a second interface in which you have to put the input data, the velocity range, the characteristic of the test facility, some constraints related to the availability of leaving the cylinder moving, or if there are walls and you have to limit the movement of the cylinder itself. And then you have just to click this button, compute, and you will obtain some results. And in these results, you can see the device dimension. So the design of the device is provided by this application. And then you have some information on the materials, on the electric power that you can extract. And here you can see this small graph, but as a consequence of the interaction with our stakeholders, Mike here in premise, we have seen that this graph is the really important thing, because this graph tell us, depending on the fluid velocity on the x-axis, how much power, how much electric power we can expect to extract from the device. In this case, it's quite a big application, we could say. So with high velocity, 2 meters per second, and a channel that is 1 meter and has a width of 1 meter, so quite big. It's not a piping application. And in this case, the power that can be extracted is quite important, roughly 150 watts. Not milliwatts, but watts, so real power. It's not big hydropower production, but it's useful to feed sensors. So this is all. This is the outcome of our work package 4 on the design. And this is the starting point of our discussion. So I would like to invite here on the floor our first panelist, Mike Hayes. He's already presented himself in the presentation, but as you have seen, he's a recognized technology leader developing power IoT solution. He worked for 20 years in power electronics industry before joining Tyndall in 2008. And he is currently head of the group ICT for Energy Efficiency there. He is involved in several projects, as you have seen, so he can really provide us a contribution in this discussion. The second panelist is Dr. Franco Masanello. He's a very well-known entrepreneur who has been able to integrate his entrepreneurial propensity with social commitment, because he is not only founder of 2 companies specialized in the provision of services in the integrated water cycle, BM Tecnologie Industriali and to have water venture. But he was also creator of important social association that assist autistic children and their family. Since January 2025, he is also the CEO of a company born from the two previous one, which is Alma Viva Blue SPA, Società Benefit. So he's really working in this field, and he can provide us the insight from the technology user. The last panelist is online, is Professor Urban Lundin. Is a member of our consortium. We expect him to be here today, but he has some issues in his company, because he is not only a professor at the Uppsala University, working in the field of magnetic forces, design of large generators and their interaction with the electrical grid, but he also is also the co-founder and the co-inventor of the active magnetic balancing, and co-founder, as I said, of the company Maxstrom, which delivers the product originating from research at Uppsala University. They have some issues at the company, so he was forced to be there, and he couldn't join us today. So can you hear us, Urban?
I can hear you loud and clear.
Thank you very much. So this is our panel, and I would like to start with the first question for Franco Masanello. We have discussed about several things, but I would like to understand the final goal, for example, of the H-Hope harvester is to feed sensors, so to produce power for feeding sensor. But you, as an user of this sensor for the services that you are providing to the network, what are the challenges related to the digitalization of the network? Because we are discussing a lot of how it would be great to digitalize network. You are already doing this, but I think it's not an easy task to do it.
Thank you very much for the invitation. There are someone in the audience that I know that are my customer. 2 words about Alma Viva Blue. Alma Viva, we are part of Alma Viva Group, is largest maybe IT Italian company. Is an heritage for what concern a country heritage for what concern digitalization, public administration. Is a company with 1.5 billion euro revenue. We are present maybe in over 30 countries around the world, and 52,000 employees, and 7,000 are in Italy. We are a vertical company for what concern monitoring waterworks and sewer channel. We are user but also manufacturer of sensor, and the big challenge in my point of view is when we talk about massive monitoring. It means not 100, 200 sensor, but 1,000, 1,000, and 1,000. This device, in this moment, we are installed in Italy around 25,000 sensors, both in the waterworks, so it means in the pipe for potable water. Normally, we're monitoring flow and pressure and leaks. And yesterday, during our call, I take the opportunity to take with me some device just for try to explain better what does it mean. It's a noise logger. It's made by us. Acoustic sensor for listening the noise generated by leaks. and triaxial accelerator for detect the movement of a pipe in oscillation of the pipe. Theoretically, in Italy, we can install over 2 million, 5 per kilometer. The question is how we can power it, the sensor. It's a very low, we work in two ways. Low absorption, so we design, the consumption is really nothing. And the other point is how we can power it. Normally we use a battery. It's a 5-6 year battery life. It's enough. But the big power absorption is during the transmission. And here, for example, we are more focused in the NB-IoT because we install underground. So LoRa is a really interesting network, but it depends also from the capability to send out from the manhole the signal. It's one problem. It's another device that we produce from next month directly in Padua. It's smart metering. We saw someone before. Also, it's in NB-IoT. The battery life here is 13 years. It's a mandatory from the regulation. So we can't provide smart metering with the battery life below 13 years. Honestly, it's a theoretical calculation because this device do not exist in the world. One device like this installed 13 years ago. So, but we choose to use to build up both simultaneously. It's an NB-IoT. It's also LoRaWAN. Because when we talk about LoRaWAN, for me, it's my mind go directly to think to smart city. We can address in the network not only information about water market, traffic, parking, public light, and sometimes it's really interesting. In this case, really, really cheaper. But in some area, there are, we call not competitive area, where is without any sense for just 2 houses build up the network. The not competitive area existing for every type of service. The school bus, for also for the aqueduct, sometimes to arrive with the water in 3-4 hours, 300 meters up is without any sense, theoretically. In that case, it's interesting to have a combination. LoRa and NB-IoT can exist together. Our idea of data transmission network is the combination. In addition, when we talk only, for example, in Italy, the 70-80% of the solution chosen from the water utility for the smart metering is NB-IoT, it's not LoRa. Why? Because for one water utility, just a water utility, they have to manage a transmission, a telecom network. Why you have to do here simple SIM? I don't have to do nothing, and the price is very low. We have a contract, just for information, with the Vodafone UK, 11 euros per 13 years. So less than €1 per year. So I think that the water utility can choose the best one for them. But returning, the energy consumption is during the data transmission. And I put in comparison both the two buff technology, NB-IoT or LoRa, because if for some reason this device is not able to send the data, it tried many times. And the battery life crashed down dramatically. But my wishes, my hope is that I don't know if in the future we can reduce again the energy consumption, because actually the level of energy consumption is very, very low, very, very low. 13 years battery life. What we need more? My hope is in the battery technology. My great expectation is that the battery technology can grow a lot. A lot. And for this device, not so much problem for what concern power of the sensor. But when we move, I'm talking, when we talk about this, I'm talking massive. So one water utility, the small one, has a plus minus, I don't know, 100,000 smart metering for billing. About this, we are talking 10,000, for example. So it's around the network, where is without any sense arrive with the energy from the national energy provider. But when we have to do, like for the PNRR, we want tender, we have to install 1,200 multi-parameter quality sensor. We can power it by battery.
Water quality sensor.
Water quality sensor. So if we have just pH or redox, okay. But when we move to turbidity, when we move to, I don't know, chlorine or dioxide chlorine, ozone, or TOC, the sensor do not exist as sensor with the low consumption. So we need to power it. And we are very attentive. We do continuously scouting on the market for check if there are some solution, maybe like yours. I don't know if the energy is possible to power the water quality multi-parameter panel, but sure we are looking for something like that. Because when we talk massive, outside the plant is simple, the energy is available, is into the network, the problem, underground. And, but also we are the first company in Italy for monitoring seaware. We have 1,000 area velocity flow meter Doppler with the level battery powered in Brianza for monitoring entire network, 4,500 in Milan, 2,000 in Rome. It's a battery powered because we are always along the network, and we change the battery every 2 years. So the service is very, very easy. Very, very, we manage by big platform. We can also rebuild the data, but in that case, we are working in area velocity sensor to reduce the energy consumption, and maybe we will achieve the result next end of this year. But for some type of sensor, I'm also thinking, for example, the big irrigation network. We have to monitoring the flow in the river. We use a Doppler radar, no contact, but the battery life is 6, 8, 10 months, and we have to provide a great maintenance, service, change the battery. It's a very easy activity. So yes, for some point, monitoring the network with a sensor like that is simple. For other type of sensor is much more complicated. We use also impeller, small impeller, small turbine. When we have, but we need a delta P, and we can do it only when we have a pressure regulate valve for reduce the pressure in the network. We can use it, but to imagine, to drill the pipe, install the turbine and lose water, it's against our philosophy and the goal and the target of all the water utility. We have to reduce the water losses. So,
I see.
Not easy.
Not easy. Not easy. So, Mike, the second question is for you. We are discussing a lot about sensors, but I'm starting seeing that one big problem in terms of consumption is the IoT, so the transmission, because also the battery life is related to the frequency of the sampling of the data. So maybe 13 years refers to a very low frequency, but if you want to increase in a near real time, 13 years are a dream, I think. Anyway, do you really think from your expertise that we have a real chance in the future, not HOPE, but more in general, to have a self-powered, near real-time monitoring system in our networks, or it's a dream?
Okay, so there's no short answer to that. I do believe that many applications, including water monitoring, can ultimately be self-powered, but we got some great examples there of what I call the chain, the power chain. So there's always a weak link in the chain. In some of the examples that you gave there, the weak link was, for example, the wireless communication network. In other cases, it's the sensor requires a lot of power. In other cases, there's problems associated with the lifetime associated with the battery. So this is why the ecosystem is so important. And again, you gave a great example there whereby you merged NB-IoT with LoRa and found a way to dramatically reduce the energy footprint associated with transceiving data. That's one of the ideas that we've actually got. We call it a little big infrastructure. The idea is that if you've got nodes like this, wireless sensor nodes buried like this, find out what's the lowest energy way of getting that data out of there in the ground or wherever it is to somewhere nearby that might have a bigger battery bank or may have an AC voltage source available to it. So it's like a lifeboat. You got to figure out how do I get the energy out, or how do I minimize the energy to do the processing that I need to do, at the edge. Another bottleneck can be the processing of the data. So very often the research challenge is it more energy efficient to process the data at the edge and then transmit the processed data, or is it more energy efficient to just send the data and not have the overhead associated with the processing? The big message there is that, and I talked about it in my slides, this is Pareto, 80% of the potential savings in power at the very early conceptual stages. So before you pick your wireless architecture, before you select your sensors, before you select your sensing intervals, before you select your microcontrollers, get all the stakeholders together and get them to work together. Then also assess what are the ambient energies available to you. I do believe that there are many, many opportunities where we will be able to self-power. We've heard, for example, the acoustic sensors that you use, because they're not on very often, it's not a big factor. But if you're using things like ultrasonic sensors, and if you want them to be on in real time, that's a big, big challenge. High energy footprint on for long periods. So we need to find ways to minimize the on-time of these sensors, minimize the energy footprint associated with processing that data, and then find the most energy efficient way to actually get that information to where it's required to make the condition monitoring or to do the optimization decisions.
Thank you. Okay. Thank you. So, Urban, we were discussing about efficiency and how important it is to increase the efficiency. So going back to our harvester, according to your experience in these years of project, what were the biggest challenges in designing this harvester and in keeping the efficiency of the system quite high?
Thank you. Sorry, I couldn't be there. I think us if I speak for all the technical VPs of this project, we do face similar challenges. One is that the concept is fairly clear, but I would say that there are too many options to realize the concept in actual hardware and the actual device. So when we realize the concept, we have to think, okay, because of a low power, what are the frictions in different parts? We want to maximize efficiency, like I said. Where do we put bearings, fixations? What about the shape of the harvester? So as always, when we do development, we have to do iterative stages. But I think a big challenge is really to realize the concept into mechanical design, which is both efficient, but also maximizes the objectives of the harvester. We have to keep in focus what these harvesters are supposed to do. And at the same time, good engineering can overcome some of that, but how do we maintain this device? If it's put in very inaccessible locations, like we heard lots of examples about, what about the longevity? What's the expected lifetime of the device themselves? So all of these will then impact the design that we will actually propose in the end. But I think right now we're at the iterative stage, that we have some concepts, we have some tests done, but who knows what the final outcome will look like and the most optimal one. We're not there yet.
Okay, thank you, Urban. So we are talking around and about consumption, sensor, and so on. But I think that one important point is also to understand the frequency of the sampling. I was saying this before. On the basis of your experience, I think it will depend on the sensor we are considering, a smart meter, acoustic sensor, water quality. Is it necessary to have near real-time monitoring for all of these sensors? Or, as Mike said, we can sit around the table and say, okay, for these sensors, it's more than enough to have one data every 15 minutes, and for these others, we need a near real time.
Good question. No, we don't need...
if you can...
sorry. Generally, in our experience, we have to choose the frequency sampling, knowing the customer process. When we talk about leak detection, in our country, average leaks is 32%. When we find the leaks, normally, the water utility needs 2 or 3 days for repair. If we use a noise logger, we find every day, every night, we find leaks. But the reaction time is not immediately. The reaction time, just for example, for the leaks is when we do not do leak detection activity, but is when the customer, the citizen, remain without water because there is a big drop of the pressure. In this case, it's the customer that do this activity. And the water utility are organized for go immediately because it's an emergency. So the customer is without water, and this activity is also regulated from the water authority area with the macro indicator M2, for example. But so it's without any sense for leak detection to talk about near real time, without any sense, in my point of view. In addition, when we use this device, it works only in the night for just 1 hour, between 3 to 4, when no additional noise, no interference, because it can listen every kind of noise. And so it's clear that is for our approach is a permanent installation forever for monitoring continuously the leaks, the new leaks. The challenge is repair the leaks more faster than new leaks appear. but it's not easy because we are really totally busy in the water market. It's a very hard work, the activity that the water utility has to do, because we are talking pipe that is underground. In Italy, between 400 to 500,000 kilometers of pressurized pipe are underground. Not easy to find, not easy to locate. So when we talk about early warning, it's important the near real time. Could be that someone can decide to put, I don't know, oil into the pressure pipe, a terrorism attack. It's important to have an early warning system. In this case, it's important how we work when change the water matrix. We do not send the data continuously if the pH is always, I don't know, 6.5. When move to 8 or move to 4, we send the data for save energy. But in this case, normally the sampling is every 15 minutes. We have also to think about, I don't know in English, inertia.
Inertia.
Inertial. The inertial process in the water are very, very big. Not easy to see big changement. The other point is for monitoring the flow in the seaward channel in Brianza, in Monza, we have around 1,000 average velocity flow meter. We get the data sampling every 15 minutes, and we send the data every 4 hours. The network, just for example, send to us 700 million data per year to our platform. And we have installed also 120 rain gauge, because we have to combine the data between the black water and the rainwater. In this case, in some area, normally also the rain gauge, when started to detect water, we have data logger every 4 hours send the data. It's important for mathematical modeling and so on. But in some area where the customer know that there are frequently flooded events, in this case, when started to rain, we send the data immediately. And the data will be sent to the water utility and the civil protection, because some area in Monza is very, very dangerous. So the early warning, the near real time, when we talk about monitoring, not automation, automation is total other things. It has sense when there are risk for the life of the people or risk for the infrastructure. For the rest, I don't see all. In addition, the other challenge, in my point of view, returning to the question before, is that now we are working for introduce the intelligence inside the sensor and not in the platform, for reduce the quantity of data that is a pre-analysis, for avoid to use all the energy for sending the data. So, in near real time or not, depend case by case, but in generally, when we talk about monitoring and not automation, I don't know if something really changed if I get a sample every 5 minutes instead of every 10 minutes for the inertia of the process. In addition, the water, the aqueduct follow the anthropic behavior. So really to predict. And after some months of data, it's easy to generate a digital twin to reply the same scenario.
I see. Mike, we are again coming back to the fact that it does not make sense to search for the perfect energy harvester enabling near real-time monitoring system if it is not necessary to have a near monitoring time. And as you said before, if maybe the stakeholders are not interested because there is not a business model in it. So can we really think that we can put together all the stakeholders and maybe work together to find a business model that makes sense for everyone, so that we can really create this ecosystem?
Yeah, I think the short answer is yes for most applications, but I think everybody's got to come out of their comfort zone, all right? So, for example, I hear the word near real time being used here. I would challenge people to try and avoid using that term. I would challenge you to try and use the word timely instead of near real time. So in some cases, you need very, very low latency. You need to know very quickly that something has happened and you need to take action. In other cases, the default, for example, a leak could be there for a long time. So, you know, you don't need to find out immediately, but you need to capture that. So you need to think about, what am I sensing? What data do I need to process? How immediately do I need that data to take the predictive or the preventative action? Most of the applications are, you know, condition monitoring, predictive, preventative maintenance. So we need to be sympathetic to the energy that's available, you know, whether it's a battery or an energy harvesting source. But I do believe that if all the stakeholders come together and have an intelligent discussion between them, we can come up with ways of making these sensors timely so that we can capture the sensor information and process it and transceive it in time for us to make the savings associated with leakage or faults or drops in pressure or whatever. So I think that's the way we need to approach it. One other quick comment I would make is I think software algorithms have a big role to play here because you know, we can use algorithms, and I showed it in the test bed in my slides there. We are trying to make the sensing intervals and the processing and the transceiving intervals dynamic. So when you capture information, use the software to determine, have I seen any change in behavior here? Is it what I expected based on behavior of neighboring sensors, based on historical data, based on the sensory data I expect? On the basis of that, do I need to process this data? Do I need to transceive this data now, or can I just send it at the end of the day or whatever when I have more energy available? How much energy is available for me if you really need this information right now? Maybe if I'm, for example, using a solar panel, you know, I might have more energy available at the end of the day or early tomorrow to do that. So that's why, you know, I promote the whole idea of the ecosystem coming together, those who can provide the power sources, those who are doing the processing of the data, those who are looking at the wireless sensor infrastructure for transceiving of data, the people who are running the networks, how immediately do they need the data? Maybe in some cases they'll actually need more data, that based on anomalies they see, they may have to crank it up and measure more intensively for a short period to see, you know, if there's an anomaly there or not, and if we need to take action or not, and then revert back to a more normal sensing interval of 15 minutes or whatever.
Okay.
You know, so I think what I call context awareness, being aware of the energy that's available, the application, the trend, the data that we're seeing there, that really tells us whether we need to, you know, what way do we send the data in a timely, not real time, in a timely manner.
Okay. Makes sense. Urban, if you don't mind, if since we are running out of time, I would like to see if there are any questions from the audience. I have other questions for you, but time is short. So is there anyone with question for our panelists? Okay, I don't see any hands. Yes, most probably. So last question for you, Urban. Do you think that we can also work on something that can have a long life to minimize the impact of potential maintenance on the network? Because it's also a matter of maintenance, we have seen. So if you want to replace the battery, or at least to be integrated in a battery, extending the life of a battery, we also need to guarantee some kind of reliability of our device.
I would say the simple answer to that is to make the device as simple as possible. I mean, we have modern tools that makes it possible to calculate, for instance, fatigue and so on. But we also have to, in order for those to provide an answer that's reliable, we also have to know the forces that this equipment is challenged by. And that's not always the case. What are the extreme scenarios that these devices will be put in? So knowledge of the actual forces, but then making designs as simple as possible. That would be my very short answer to how we solve this issue.
Thank you for the answer and also for being very short. The audience, thank you, because this panel is arrived at an end. Thank you very much to all of you, to Mike, Franco, and Urban online. It was a pleasure to have you here. And I think that we can stop here, and there is a coffee break waiting for you in the lobby over there. Thank you very much.